In this section, we will learn to solve a variety of equations, including polynomial equations, rational equations, radical equations, equations with radical exponents, and equations in different quadratic forms. Let's begin with the technique called grouping. When you group, you group two together at a time. So if I look at this equation, x cubed plus 8x squared minus 9x minus 72 equals 0, I'm going to group the first two terms together, x cubed plus 8x squared, and then I want to group the last two terms together. I'm going to use a plus sign in the middle here and leave the negative with the 9x. So it's plus parentheses negative 9x minus 72, that in parentheses, equals 0. Next, you want to factor out the GCF from each of the two different parts. The first part, I have a GCF of x squared, and that leaves x plus 8. And in the second part, I have a GCF of negative 9. So I'm going to factor out the negative 9. This is where the negative comes into play. The first part leaves me with an x. If I factor out a negative 9 from a negative 72, that leaves me with plus 8 equals 0. Now the trick to grouping is to ensure that you get the same piece on both parts. Here we have x plus 8. That x plus 8 is going to factor out in front of everything. And then that would leave on the left the x squared. The x plus 8 has already been factored out. On the right part, we have a negative 9, and the x plus 8 has been factored out. Now we have x plus 8 times x squared minus 9. Well, x squared plus 9 also factors. That's the difference of two squares, and that's x minus 3 and x plus 3. And then if we were to set each of these equal to 0, we get x plus 8 equals 0, x minus 3 equals 0, and x plus 3 equals 0. We get x equals negative 8, x equals positive 3, and x equals negative 3. So the solution set is negative 8, 3, and negative 3. And of course you could write that as plus or minus 3 if you'd like. In example 2, we want to solve for w. The equation is 2w cubed minus 3w squared plus 8w minus 12 equals 0. We're going to use grouping again on this. So I'm going to group together 2w cubed minus 3w squared plus, parentheses, 8w minus 12 equals 0. I can factor out a w squared from the first part. That leaves me with 2w minus 3. And on the right part, I can factor out a 4. And that leaves me with 2w minus 3. Now, not everything will factor by grouping, but when they do, it works out really well. You must have these parts be the same. So we have 2w minus 3 and 2w minus 3, so that factors out to the front, 2w minus 3, times what's left over, which is w squared plus 4. So that equal to 0. Now we can split this up, set each factor equal to 0. 2w minus 3 equals 0, and w squared plus 4 equals 0. Working on the left-hand side, I'm going to move the 3 over and solve for w over here. Divide by 2, and we get 3 halves. On the right side, I'll move the 4 over. It goes over as a negative. So we have w squared equals negative 4. Take the square root of both sides, and I get w is equal to plus or minus the square root of negative 4. Since we're taking the square root of a negative number, we end up with an I, and then the square root of 4 is 2. So this is plus or minus 2I, and the solution set is 3/2 and plus or minus 2I. On page 2, we look at a technique of factoring out the GCF. In example 3, we want to solve for m. 3m to the 4th is equal to 48m to the 6th. I'm going to start by moving the 48m to the 6th to the left side. That gives me 3m to the 4th minus 48m to the 6th equals 0. We need to figure out what the GCF is. The 3 and the 48 are both divisible by 3, so we can take that out. And then we can always take out the smallest exponent of the variable. So we have m to the 4th and m to the 6th. That means I can take out m to the 4th. So if I factor out 3m to the 4th from 3m to the 4th, I have to put something there to mark that that was there. And of course, we use a 1. You have to be able to redistribute this to get back to the previous level if you're going to check it. So the question really is, what times 3m to the 4th is equal to 3m to the 4th? Of course, that's a 1. Minus 48 divided by 3 is 16. And then m to the 4th times what is equal to m to the 6th? That would be m squared. Now notice that 1 minus 16m squared is the difference of two squares. 1 is a square and 16m squared is a square as well. So I'm going to go ahead and factor that. That factors as 1 minus 4m and 1 plus 4m. Next, let's set each factor equal to 0. So 3 equals 0. M to the 4th is equal to 0. 1 minus 4m equals 0. And 1 plus 4m equals 0. 3 equals 0 is false, so discard that. M to the 4th is equal to 0 only gives the solution m equals 0. 1 minus 4m equals 0. I'm going to move the 1 to the other side and then divide by negative 4. And that gives me m equals 1/4. And then I'll solve the last equation. 1 plus 4m equals 0. I'm going to move the 1 to the other side and then divide by 4. We get m is equal to negative 1/4. So the solution set here is 0. And I'll go ahead and write this condensed here, plus or minus 1/4. Let's take a look at example 4. Solve for x. 2x to the 4th is equal to 250x. Again, we'll start by moving everything to the left so that we have a 0 on the other side. We always need zeros on the other side. The GCF here is 2x. So I'm going to factor that out, and that's going to leave x cubed minus 125 equals 0. And then notice that the second factor is x cubed minus 125. I'll remind you that this is called the difference of two cubes. And the formula for the difference of two cubes is a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. So if you've forgotten that, make sure you remember that. There's also a sum of two cubes. I'll leave it to you to look that one up. It's basically the same formula with some signs changed. But we need to factor this second piece. And so the x is the first part being cubed, and then 125 is 5 cubed. So that's x minus 5 times, and then we just use the x and the 5 again. We have x squared plus the 5 times the x plus 5 squared, which is 25. Now we set each factor equal to 0. So we have 2 equals 0, x equals 0, x minus 5 equals 0, and x squared plus 5x plus 25 equals 0. Two equals 0 doesn't make any sense. Discard that. X equals 0 is done. X minus 5 equals 0 gives me x equals 5. And then the last one, let's go ahead and move that over here and solve it. It's a quadratic. Since it came from the difference of two cubes, and the highest power in the original cube was actually a cube, it was x to the third power, then this one will always have imaginary answers. So we'll go ahead and use the quadratic formula on that. It's going to be negative 5 plus or minus the square root of 5 squared minus 4 times 1 times 25 divided by 2 times 1. This gives me negative 5 plus or minus the square root of 25 minus 100 over 2. Simplifying the inside of the square root, we get negative 5 plus or minus the square root of negative 75 over 2. Then we have negative 5 plus or minus. We have a negative under the square root, so that comes out as I. 75 is 25 times 3. So we take the square root of the 25, that's 5, but the 3 stays on the inside. So it's 5I root 3 divided by 2. You could factor out the 5, but since it's 5, both 5's on top, but since the denominator doesn't contain a 5, there's no use in factoring that out. It won't be able to cancel with anything, so we just leave it there. So the solution set is 0, 5, and then minus 5 plus or minus 5I root 3 over 2. In example 5, we have a rational equation. We have fractions and we have variables in the denominator. As we know, we have to look for restricted values, values that the solution cannot be. The first step here is going to be to factor this denominator on the right, and it's going to be k plus 4 times k minus 1. If you set each denominator equal to 0 and solve, you'll get these restricted values. From the left one you get k equals negative 4, from the middle one you get k equals 1, and from the one on the right you just get negative 4 and 1 again. So we can't have k is equal to negative 4 or negative 1. Alright, to solve this we need to compute the least common denominator. Of course that's going to be k plus 4 times k minus 1. And then we will multiply both sides of the equation by k plus 4 times k minus 1. So k plus 4 times k minus 1 times 3k over k plus 4 minus 3 over k minus 1 is equal to k plus 4 times k minus 1 times 2k squared minus 8 over, and I'll use the factored version here, k plus 4 times k minus 1. Next, on the left side, I'm going to distribute the LCD to both terms. So we're going to have k plus 4 times k minus 1 times 3k over k plus 4 minus, and then the LCD is distributed, k plus 4 times k minus 1 times 3 over k minus 1 is equal to, and nothing to do on the right side, k plus 4 k minus 1 times 2k squared minus 8 over k plus 4 times k minus 1. Next, let's cancel the denominators with the LCD. So in the first one, we have k plus 4 cancels, and that leaves 3k times k minus 1. Next, the k minus 1 cancels, and that leaves 3 times k plus 4 is equal to, and on the right side, both parts of the denominator cancel, and that just leaves the numerator, 2k squared minus 8. So we've gotten rid of all the denominators. Let's go ahead and distribute. On the left here, we have 3k squared minus 3k. Distributing the negative 3, we get minus 3k minus 12 is equal to 2k squared minus 8. We have a quadratic. Since the highest power is squared, we have k squared. So we need to move everything to the left and have a 0 on the right. When the 2k squared comes from the right to the left, it becomes negative. We have 3k squared on the right, so we have 3 minus 2 is 1. So we get 1k squared. There are no k terms on the right side, so on the left we just have minus 6k. And then lastly, we have negative 8 on the right. We move that over to the left, it becomes positive, combines with the negative 12, and gives us negative 4. You could try to factor this one, but it's not going to work. So let's go ahead and use the quadratic formula. So we get k is equal to negative 6 plus or minus the square root of negative 6 squared minus 4 times 1 times negative 4 over 2 times 1. Simplify. Negative 6 is positive 6. Plus or minus. Negative 6 squared is 36. Negative 4 times 1 times negative 4 is positive 16. 2 times 1 is 2. 36 and 16 combine as 52. And then 52, I'll work this out on the side for you. 52 is really 4 times 13. So this is 4 times 13 over 2. We can take the square root of 4, but we cannot take the square root of 13. The square root of 4 is 2, so 2 comes out, 13 stays inside. We have 2. Now, notice that you have two terms on top. You have the 6, and then you have 2 root 13. You also have a 2 on the bottom. So all three of those are multiples of 2. So we have to factor out a 2 from the top so that we can cancel it with the 2 on the bottom. It's just like reducing a fraction, but you have to factor out first. You can't just come in and cancel some 2's that you see there, because it's not just 2 over 2. It's 6 plus or minus 2 root 13. So we're going to factor out a 2. That leaves 3 plus or minus root 13 over 2. And then the 2's cancel. And that leaves 3 plus or minus the square root of 13. And that's the solution. Let's look at example 6 on the next page. Again, we have a rational equation, so we need to compute the restricted values. I'm going to factor this denominator here. Factors is x minus 5 and x plus 1. And if we set each of those denominator factors equal to 0 and solve, we would get x equals 5 and x equals negative 1. So these are the ones that x cannot be. X cannot be 5 or negative 1. The LCD again is x minus 5 times x plus 1. So we're going to multiply both sides of the equation by the LCD. So we have x minus 5 times x plus 1 times 3x over x minus 5. And that is equal to x minus 5 times x plus 1 times, the right side is 2 over x plus 1 plus 2x squared plus 40 over, I'll write this as factored in the factored form, x minus 5 times x plus 1. We need to distribute the LCD on the right side. The left side stays the same. So I'm going to distribute x minus 5 times x plus 1 times 2 over x plus 1 plus, and then the LCD again, x minus 5 times x plus 1 times 2x squared plus 40 over x minus 5 times x plus 1. Now, we need to cancel, get rid of the denominators. On the left side, x minus 5 cancels, and that leaves me with 3x times x plus 1 across the equal sign. X plus 1 cancels, leaving me with 2 times x minus 5. And lastly, both parts of the denominator cancel, and that leaves me with plus 2x squared plus 40. The next step is to distribute the 3x here on the left, so we have 3x squared plus 3x. Then we have on the right side distributing the 2, we have 2x minus 10, and then of course 2x squared plus 40. Think about what kind of equation we have. It is a quadratic. When you have a quadratic or higher, you need to move everything to the left and get a 0 on one side. On the left side we have 3x squared. On the right side we have 2x squared. The 2x squared comes over to the right and subtracts and leaves us with 1x squared. On the left we have 3x. On the right we have 2x. The 2x comes over and subtracts and leaves us with 1x. On the right side we have negative 10 plus 40. That would be positive 30. When positive 30 moves over to the left side, it moves over as a negative. So we end up with x squared plus x minus 30 equals 0. This one will factor. So I'm going to set up x and x. Then what two numbers multiply to give you 30 and subtract to give you 1? That would be 5 and 6. To make positive 1 in the middle, positive 1x rather, we need a positive 6 and a minus 5. Split this up and set each factor equal to 0. And we get x equals 5 and x equals negative 6. But wait, remember that negative 5 was one of the restricted values. So this is not a solution. So that one is out. The only value that actually works is x equals negative 6. So that shows us the importance of checking the restricted values before we begin the problem. That way we can know if we have an answer or not. In this part of the lesson, we're going to solve radical equations. What is a radical? A radical is the term for the square root is a radical, and then cube root is a radical, and fourth root, etc. And in fact, sometimes you hear people talk about the nth root. It's the nth root. So square root is reserved only for this first symbol. And the numbers that go inside of these radicals is called the index, and it tells you what root you are taking, whether it's a cube root, fourth root, or nth root. That is called the index of the radical. Here are some tips for solving radical equations. Number 1, isolate the radical on one side of the equation. Step 2, raise each side of the equation to the power of the index of the radical. So essentially that is the opposite of taking the nth root, you raise it to the nth power. So if you have a square root, then you'll square both sides. If you have a cube root, then you will cube both sides. Step 3, repeat the first two steps until there are no more radicals. You could have an equation that has multiple radicals in it, and you'll have to work with that some to get rid of all the radicals. And step 4, solve the equation that's left over, and then check your solution. When you start raising parts of equations to powers, you must check the solution. You can end up with what we call an extraneous root. And so you'll definitely need to check the solutions on each of these. Let's look at example 7. Solve for x. We have the square root of x plus 5, and then plus 7 outside the radical is equal to x. So step 1 is isolate the radical on one side of the equation. So I'm going to leave square root of x plus 5 on the left. I'm going to move the 7 to the other side. It moves over as a negative. Step 2, raise each side of the equation to the power of the index of the radical. Since we're dealing with a square root, and remember the 2 is not written on a square root, when the radical is presented without an index, it's understood to be index 2, which is a square root. So we're going to raise both sides to the second power. We're going to square them. On the left side, taking the square root of x plus 5 and squaring it afterwards, those are opposite, and so they cancel. On the right side, we'll use our trick. X minus 7 squared is x squared minus 14x plus 49. Look at the equation that you have. It is quadratic, so we're going to move everything to one side. I choose for this one to move everything to the right side, leaving a 0 on the left. We only have the one x squared term. The x on the left moves over to the right as a negative x. That combines with negative 14x, giving me negative 15x. The 5 from the left moves over to the right as a negative, and then 49 minus 5 is 44. X squared minus 15x plus 44 factors. That gives me x and x. And then what two numbers multiply to give you 44 and add to give you 15? That would be 11 and 4. Both of them are minus. And then if you set each of these factors equal to 0, you will get x equals 11 and x equals 4. Now, because we squared the equation above, we must check it and see if our solutions are still valid. You are only allowed to check it in the original equation before you have altered it in any way. So there's the original equation. The square root of x plus 5 plus 7 equals x. First, I'm going to check x equals 11. And the way we do this is we plug in the value of x. I'll use a special equal sign that has a question mark on top. And then we just verify that the left side simplifies and the right side simplifies, and they both simplify to the same thing. On the left side, 11 plus 5 is 16, so we have square root of 16 plus 7 might be equal to 11. The square root of 16 is 4 plus 7. That might be equal to 11. And in fact, 4 and 7 is 11. That one checks out. So therefore, x equals 11 works. Let's check the other solution. So let's check x equals 4. So we have the square root of 4 plus 5 plus 7 might be equal to 4. The square root of 4 plus 5 is 9 plus 7 might be equal to 4. Square root of 9 is 3 plus 7 might be equal to 4. So we have 10 and 4, and those are not equal. So therefore, the 4 does not check out. So the only solution here, the solution set, is 11. The 4 is discarded as an extraneous root. In example 8, we have solve for x. The square root of 2x plus 1 minus the square root of x is equal to 1. We have two radicals here, so the trick is going to be to isolate one radical and by moving everything else to the other side and squaring to get rid of that radical, and then we'll still have one radical left over and we'll repeat the process. In general, the easiest thing to do is take the most complicated radical to be the one that is isolated on one side of the equation first. The most complicated one is the square root of 2x plus 1. So we're going to leave that on the left by itself and move the square root of x to the other side. Next, we square both sides. Now the right side has two terms, so we'll have to use our trick for squaring two terms to work out the right side. On the left side, the square root and the square cancel. On the right side, we square the square root of x, which is x, and multiply 2 times square root of x times 1. There's 2 square roots of x, plus, and then 1 squared is 1. Now to simplify, First, notice that we have plus 1 on both sides, so that cancels. And then next we have 2x on the left and x on the right. So 2x minus x is x, and then 2 squares of x stay on the right. Again, we have a radical, so the trick is to square both sides. So I'm going to square the x, and then I'm going to square 2 times the square root of x. The left side is still just x squared. The right side, we must square both the 2 and the square root of x. So 2 squared is 4, square root of x squared is x. We have a quadratic, so we need to move the 4x to the left. We get x squared minus 4x equals 0. From here, we're going to factor out x. We get x times x minus 4 equals 0. Split up the factors and set them equal to 0. X equals 0 is done, and then x is equal to 4. Next, we need to check both of these answers. So let's check x equals 0. So I'll remind you of the original equation. So square root of 2x plus 1 minus the square root of x equals 1. So to check x equals 0, we'll plug in 0 for x. So we have the square root of 2 times 0 plus 1 minus the square root of 0 might be equal to 1. I need to simplify the left side. So 2 times 0 plus 1 is 1, minus the square root of 0, that might be equal to 1. Square root of 1 is 1, square root of 0 is 0, that's equal to 1. And so we have 1 is equal to 1. That checks out. So 0 works. Next, let's check x equals 4. So we have the square root of 2 times 4 plus 1 minus the square root of 4. That might be equal to 1. Under the first square root, we have 2 times 4 plus 1. That's 9, so we have square root of 9. Minus the square root of 4. That might be equal to 1. Square root of 9 is 3. Square root of 4 is 2. Might be equal to 1. 3 minus 2 is 1. Equals 1. And that one works out as well. So this is a case where both of the answers we got worked out. In fact, you can have any sort of arrangement possible. You can have it where you have both answers work out. You can have it where one works, the other one doesn't. You can even have it where neither answer works and you have no solution. So our solution set for this problem is 0, 4. 0 and 4. Next, let's look at solving equations with rational exponents. Remember, rational number is an integer divided by an integer. So we're looking at things that are x raised to the m over n power. And that can be rewritten in either of these following ways. The nth root of x to the m power, where the m is on the inside with the x, and under the nth root, or you can take the nth root first of just x and then raise that result to the m power. This one we'll use a lot because it creates smaller numbers in general. Now, one way to think about this fraction is power over root. And so what I like to draw is, x to the m over n, and then it turns out that this is sort of like a tree, like this. And the way you remember this is that what's in the bottom of a tree? That's right, the root. And what can be up in the top of the tree? Yeah, the little power lines. So that's where the m is for the power. So it's power over root. So just remember that's the order of things. Example 9, solve for u. We have u raised to the 3/4 power equals 27. So the trick here, of course, is that you want to get u to be u to the first power. To get rid of this power that is the 3/4 power, we need to raise both sides to the same power that will knock out the 3/4. And to do that, we're going to raise it to the reciprocal power. So we're going to raise it to the 4/3 power. So on the left, we have u to the 3/4 to the 4/3. Remember, if you were simplifying that, you would multiply those exponents together. 3/4 times 4/3 is 1. So this is just u. And this is now equal to 27 to the 4/3 power. I'm going to convert that to one of our radical forms. The 3 in the bottom is the root, so that's the cube root of 27. And then the power, the 4 on the outside, is the power outside of that parentheses. And then the cube root of 27 is 3. And then 3 to the 4th is 81. So the solution here is 81. In example 10, solve for y. We have y to the 2/5 power is equal to 1/4. So we'll employ the same trick again. Start with y to the 2/5, leave some space, is equal to 1/4. I need to raise this to a power that will knock out the 2/5 power. And of course we choose the reciprocal, 5/2. So y to the 2/5 to the 5/2, you would multiply the exponents. 2/5 times 5/2 is 1. So we're left with y equals, and then we have 1/4 to the 5/2 power. Now this is going to be, the 2 on the bottom represents the 2 root, which is the square root. So it's the square root of 1/4 raised to the 5th. When you take the square root of a fraction, you take the square root of the numerator and the square root of the denominator. The square root of 1 is 1, the square root of 4 is 2, and then we raise that to the 5th power. And then when you raise a fraction to a power, you split that power up among both the numerator and denominator. So we get 1 to the 5th is 1, and 2 to the 5th is 32. Now, go back and look at the original exponent here. The y was being raised to the 2/5 power. When the power part of the power over root is equal to an even number, as in the 2, then our answers must include a plus or minus, because the even power means that whatever was done before that could have been positive or negative, and then it was either squared or raised to the 4th power or the 6th power, and then it automatically became positive because of that. So we don't know if it was positive or negative to start with, so we indicate that it could be positive or negative in the end. So the solution is plus or minus 1/32. Example 11 works pretty much the same way. We have 5a minus 4, all raised to the 5/3 power, is equal to negative 1024. I'm going to start with 5a minus 4 raised to the 5/3 power is equal to negative 1024. We're going to raise it to the reciprocal power on both sides. That leaves 5a minus 4 is equal to the 5th root of negative 1024 cubed. So we have 5a minus 4 is equal to, the 5th root of 1024 is 4. If you have a negative number that was raised to the 5th power, the result is still negative. So if you have a negative number that's being you're taking the fifth root of that, the answer is still negative. Still negative because fifth root is an odd root. Then we have 5a minus 4 equals negative 4 cubed. And negative 4 cubed is negative 64. Move the 4 over, you get 5a is equal to negative 60. And a little bit out of space here, so I'll write it over here. Divide both sides by 5, you get a is equal to negative 12. And that's the solution. We don't have to worry about the plus or minus because we didn't have an even power. In the next section, we're going to solve quadratic-like equations. If we look at this example, example 12, we have x to the fourth minus 14x squared plus 45. Now this is not quadratic because the highest power is not 2. The highest power is the fourth power. But it is quadratic-like in the sense that we have this minus 14x squared in the middle, and then x to the fourth, the beginning term, can be written as this middle piece, this x squared, squared. So you have something squared minus 14 times that same something plus 45. So that's quadratic-like. And what we're going to do is we're going to use a method called substitution. And here we're going to substitute u in place of x squared. So now we're going to rewrite this equation with u in place of x squared. So the first one is x squared squared, so that's going to become u squared. Minus 14, and then we have x squared. I'm going to replace that x squared with a u. And then lastly, plus 45 equals 0. Now it reduces it back down to something that looks very much like a quadratic. It is u squared minus 14u plus 45. So this we can use all of our quadratic methods on. In fact, this one factors. So we're going to have u, and then what two numbers? Multiply to give you 45, and add to give you 14. That would be 9 and 5, and they're minus and minus. And if we solve these when we set them equal to 0, we would get 9, u equals 9, and we would get u equals 5. Now, the question is not to solve for u, the question is to solve for x. But we know what u is equal to. In this step, which I call back substitute, we back substitute back into the x. So u is equal to x squared, so x squared is equal to 9. And then x squared is equal to 5. Lastly, we solve for x. Using whatever methods we have to at this point. A variety of methods will come up in the homework exercises. This one, we just use the square root principle, property. So x is equal to plus or minus 3, and x is equal to plus or minus the square root of 5. So the solution set has 4 answers, based on x to the fourth at the beginning. It's plus or minus 3, and plus or minus root 5. Let's look at example 13. We have x squared minus x, that quantity being squared, minus 18 times x squared minus x, plus 72 equals 0. Again, this is quadratic-like because we have this x squared minus x term, and then we have that same term being squared at the beginning in this case. And so it looks sort of like a quadratic. So let's use substitution. And this time u is going to equal x squared minus x. When u is equal to x squared minus x, I can rewrite this equation as u squared minus 18u plus 72 equals 0. Again, this factors. So it's going to be u and u. And then what two numbers? Multiply to give you 72 and add to give you 18. It would be 6 and 12. And we split these up and solve for u. So u is equal to 6 and u is equal to 12. Now we back substitute. And I'm going to write it over here. So we get x squared minus x equals 6, and x squared minus x equals 12. Let me solve the one on the left first. If we have x squared minus x equals 6, I can move the 6 over. It comes over as a negative, and then factor. So we get x and x, 3 and 2, and we have to subtract. We need 3 to be the negative, so it's going to be x minus 3 times x plus 2. That gives us the answers x equals 3 and x equals negative 2. And then the same thing on the right side. We have x squared minus x minus 12 equals 0. I can factor this. So we have x and x, and 4 and 3. We need the 4 to be negative. We solve that, we get x equals 4 and x equals negative 3. So the solution set here is 3, negative 2, 4, and negative 3. In example 14, we have solve for x. X to the 2/3 power is equal to 9 times x to the 1/3 power minus 8. So we have, again, x to the 1/3, and then x to the 2/3 can be written as x to the 1/3 squared. So there's that x to the 1/3. So this is quadratic-like, and so we're going to substitute u is equal to x to the 1/3. When I substitute x equals u is equal to x to the 1/3, we're going to get u squared is equal to 9u minus 8. We have a quadratic, we move everything to the left. So we get u squared minus 9u plus 8 equals 0. I'm going to factor u and u. 8 and 1, minus and minus. When we split these up and set them equal to 0, we get u equals 1 and u equals 8. Back substitute, we get x to the 1/3 power is equal to 1, and x to the 1/3 power is equal to 8. And then to solve these, we're going to raise them to the reciprocal power, so it's going to be a 3 on both of these. And so x is equal to 1, and x is equal to 512. Now notice that when we actually went to solve x to a fractional power, that fraction was 1/3. It wasn't 2/3 like it was in the original equation. Because it was 1/3 and the 1 is odd, we don't have to worry about plus or minus. It's just positive 1 and just positive 512. So the solution set is 1 and 512.
Oh, that's so wimpy. Come on, give it all you got. Go!